welcome back. So in the last class we have discussed about our basic DC to DC converters. So we have started with our buck converter, which was our step down converter. Then we have seen our boost converter, which was our step up converter. Now we will be discussing about the third type of DC to DC converter, that is our buck boost converter. It is again a second order system. Why? Because we have two energy storage element. Okay, so we have seen the on state and off state equivalent circuit of this one. When the switch is on, the positive terminal of the supply was connected to the negative terminal of the diode, so it was getting reverse bias. So diode will remain in the off state, and this was the equivalent circuit. When the switch was in the closed state, the source will be charging the inductor, and the output side capacitor will be feeding the energy. Okay, then if I apply KVL, so we have found out the relation between our change in inductor current with respect to dt and Vs by L. Okay, so now if I write it in terms of the change in inductor current when the switch is closed, so it will be given as Vs by L into dt. Then when the switch is open, so as my inductor was charging in this direction, when the switch was closed, it will try to maintain the current in this direction, and in turn it will bring the diode in the forward bias mode. So now here the inductor will be behaving as a source and it will be driving the output stage. So now Vs, again applying KVL in this loop, I will see that the inductor voltage will be equal to the output voltage. Now again linearizing it, that is by assuming the switching frequency to be very high, I can replace the di by dt by delta L by delta t, so which will be equal to V naught by L. So now the turn off time period delta t, it is nothing but equal to 1 minus d into t. So delta IL open, when the switch is in the open condition or in the off state, it will be equal to V0 by L 1 minus d into t. So when I equate both of them, that is the change in inductor current when the switch was closed, the change in inductor current when the switch was in the open circuit condition, and we know that for steady state operation the change in inductor current must be 0, that is it should start from the same point at the start of the every cycle. So when I add them and equate it to 0, and we have observed that the relation between input and output voltage was equal to minus of Vs into d by 1 minus d. So the negative sign indicates that the output voltage will be having a reversal in the polarity, that is plus will be at the bottom side, and the duty ratio type wise, so d by 1 minus d, and we have seen what will be the outcome of this relation. Whenever my duty ratio is less than 0.5, it behaves in the buck mode. When my duty ratio is above 0.5 and limited between 1, that is 0.5 to 1, it will behave in the boost mode. Then the graphs, okay, so the voltage across the inductor. When my switch was in the closed state, I have seen that the inductor was entirely connected across the source, so it will be experiencing a voltage which is equal to the source voltage for the time 0 to dt. And when the switch is in the off condition or when the pulse is removed from it, so the inductor will be experiencing a voltage which will be equal to output voltage in the negative direction. Okay, now so how this negative has come into picture? We have seen that there will be an polarity reversal, that is this will be plus and this will be minus. So the inductor will be experiencing a negative voltage across it, and it will be behaving source or it will be getting discharged. So similarly the same conclusions can be drawn from the current graph also. So when the switch is in the closed state, the inductor is experiencing increment in energy. When it is in the open condition, it is experiencing decrement in the energy, or it is behaving as a source and feeding the energy which is present inside it. Here again we have assumed continuous conduction mode. So here inductor current will be either positive and finite. If it touches 0 at the boundary condition, it will just touch 0 at the end of the cycle. Always it will be positive. Okay. So if that is not satisfied, then it will enter into the discontinuous conduction mode, which we are not discussing right now. So now the diode current. Okay. So when the diode is carrying the current, when my switch was in the open condition or when the switch was disconnected, so the diode was carrying the current which is equal to the inductor current. Okay, so if you see during the off state, when the switch was off, my diode current is equal to the inductor current, because both of them are coming in series in this path. If you see, whichever is the current in this path, that will be the same which will be coming through this. Okay, so now if I find out the area and equalize them, I will see that the average diode current will be equal to my output current. Okay, so the average current flowing to this path will be equal to the average output current. Okay. Now minimum inductance value to maintain your CCM mode of operation. we will carry out the same operation as we are doing, that is, we will find out the minimum inductor current value, we will equate it to 0 to find out the boundary condition. So, now your average inductor current minus 50% of the ripple will be giving me the minimum inductor current value. So, determine the IL value, what will be the average inductor current value in this case. Okay. So, it will be equal to, output power will be equal to input power. So, V0 by R will be equal to Vs Is. So, now Vs Is we have this relation. Okay. So, that is the source current will be equal to IL into duty ratio times. Okay. So, now IL will be given as Vsd by R minus 1 minus d square. Okay. We will be using this in our expression for IL, and we have determined the delta IL value when the switch was in the closed condition. So, that is what we have replaced it over here, and if I equate it to 0, I will find out that L minimum will be given as 1 minus d square into R by 2f. Okay. So, if I am having an inductor which is less than this value, I will enter into the discontinuous conduction mode. If I have an inductor which is greater than this minimum inductor value, it will be in the continuous conduction mode, the current will always be positive. If it is just equal to this value, then I will see that the inductor current will touch 0 at the end of the cycle. At this point, it will return to 0 and it will remain in the continuously positive value in the entire cycle of operation. Okay. So, at the boundary of continuous and discontinuous conduction mode, it will just touch 0. Then the next parameter is our capacitor size. How to determine the capacitor size over here? Okay. So, here again Q equal to C V naught. Now, we will replace it by small change in the current will be equal to small change in the capacitor voltage. Delta Q is equal to V naught by R into dt. That is the area under this curve. Again, during that switch on period, it is feeding the output current entirely. So, it will be equal to V naught by the time duration for which it is feeding it is dt. So, this will be the area under the curve, which will be the charge which is removed from the capacitor. Okay. So, if I replace it in the expression, I will find out that the capacitor will be given as V0 dt by R by delta V naught value. Okay. So, till this point we were discussing about our unidirectional converters. What are those? They will be carrying the power in this direction only, that is from the source towards the load. Now, in some applications we will be requiring bidirectional power flow. What is the meaning of that? The power can flow from the source to the load, and in some case it can be fed back to the supply. So, what is the best example of this one? Regeneration. This is the source to your load is when your EB is in the normal operation mode, that is here we are driving the electric vehicle. Suppose now we want to, our EV was running at a particular speed, we want to stop the vehicle. So, we will have some excess energy, we can remove it and we can use it to recharge our battery, so that our battery energy will be optimized or we will be having a longer range. So, generally we operate our EV motors in the 4 quadrant operation mode, that is it will be going for regeneration. Whenever I have excess energy, I can use that to charge my vehicle. Okay. So, one is during the stop case, other example is when I am moving down hills, I will have excess energy which can be used to charge my battery bank. Okay. So, for this type of applications we require the converter to be bidirectional, that is the power should flow from the input to output or from the output to the input stage. Okay. So, now here this is the requirement of bidirectional converter. If you see, the power can be flowing from the converter to the battery bank or vice versa. Okay. Now, how to get an bidirectional buck boost converter? Okay. So, in this case, because of the presence of this diode, the current was limited in only one direction. Okay. In this buck converter, this diode, if it is present, generally our MOSFET has an body diode that was never coming in the conduction path. Why? The current direction was fixed in this converter. Okay. Suppose now I replace both of them by bidirectional current carrying devices, that is both with your MOSFETs with body diodes, or it can be an external diode based on my application. Okay, and my efficiency requirement. The body diodes will be having higher losses, so generally we connect an external diode over here. Okay, so based on our applications we can select the device over here, but it will be an bidirectional current carrying device. So here if you see, both the devices are having bidirectional features. So we say that this converter can operate in the bidirectional mode, the base converter was buck and boost. So, we say that to be an bidirectional buck boost converter. Okay. So, now let us see how this circuit will be operating. We will have two switches. Okay, during one direction of power flow we will operate one switch, and during the other direction of power flow we will operate the other switch. Suppose for example we have an DC link over here, we have an EV battery bank over here. Okay. Now if switch 1 is used and switch 2 is kept in permanently off state, the power will be flowing. So when if you see here we have a diode, because switch 2 is permanently off, so only this diode is operated and we are operating this switch. If I see the arrangement, now it has reduced to a buck converter, because there is inductor and diode. So when the switch is closed, the inductor will store the energy. When I remove the pulse from the switch, it will circulate to the diode. So it operates in the buck mode of operation, or the equivalent circuit reduced to buck mode. Now the power is flowing, in this case power is flowing into the battery bank through the DC link, or the source which is present over here, it is giving power to the EV battery bank. Okay. Now the vice versa condition, switch 1 is not given the pulse, only we are operating the switch 2. Okay. So now in this case, if you see the inductor is, when the switch 2 is closed, the inductor is getting connected across this EV battery bank. When I open the switch 2, the inductor will be discharging. So in this case, what will be the power flow direction? So if I see, the power will be flowing from the EV battery bank to the DC link converter. Whenever my switch 2 is closed, the inductor will store the energy. When I open the switch 2, it will carry the current, or it will force the current through this diode, and it will charge our DC link. Okay. So here the power is being recovered from the EV battery bank and it is being given to the DC link. Okay. So by selecting whether I am operating S1 or S2, I can control the direction of power flow in this circuit. So that's why it is called as bidirectional buck boost converter. Okay. So let us see it again by through an example. Okay. So DC link voltage is given as 800 volt. Now we have an battery bank voltage of 600 volt, and the switching frequency is assumed to be 20 kilohertz, and switch 2 is permanently off in this operating condition. Okay. So the power will be flowing because of this switch 1, and it will be flowing in this direction, that is in the buck mode. Okay. So how it will be? Now in this buck mode we know the relation between the input and output, it will be the duty ratio times of switch 1. Now because we are operating a switch 1, switch 2 is permanently off. So now it will be given as the 600 by 800. So it will be equal to 0.75. Now it will be operated in the buck mode of operation. Now suppose I want to operate it in the boost mode. Okay. The same set of values. Okay, if you see the values are the same, only thing which we have changed is the mode of operations. Now switch 1 is permanently off and switch 2 is operated at 20 kilohertz frequency. In the previous case, switch 2 was permanently off and switch was operated at 20 kilohertz. Now in this case we have flipped the operation, switch 1 is kept permanently off and switch 2 is operated at 20 kilohertz. When the switch 2 is operated, we have seen that the power will be flowing in this direction, or it will be operated in the boost mode. So now the relation between your input and output voltage, we know that it will be equal to 1 minus ds2. Okay. In this case it is ds2 will be equal to 1 minus 600 by 800 as per our given values. So we will find out that the value will be equal to 0.25. Okay. So based on my requirement, whether I want the power to flow from the source to the load or from the load to the source, I will give the pulses accordingly to my switches. Okay. So if I give the pulse to switch 1, I have observed that the power flows in this direction. When I have given the switch to pulse to S2, it flows in this direction. Okay. So generally this type of bidirectional feature is required when I want to control the power in both the directions, that is I can charge and discharge the circuit. Okay. So this example we have considered with respect to the EV battery bank. The similar activities can be done by considering that EV battery bank is over here and we have the intermediate DC link. As we have seen that our motor will be mostly an AC motor, so there we will be having a DC to AC conversion. So in between this we will be having a DC link. Okay. The EV battery and the DC link, or on the charger side as well, where my source will be connected at the input stage, where we will be having AC to DC converter. Then we will have in the intermediate DC link which will be charging the battery. So that can be used in V to G and G to V mode. So, what are these modes of operations? We will come back later on. That is bidirectional charging, where your EV can be used to support your grid. Okay, that is your vehicle to grid, where your electric vehicle is supporting the grid to reduce its peak loading conditions. These things we will see later on when we go into these discussions. Okay, the other mode, this is the normal mode of operation, grid to vehicle, or the vehicle is getting charged. Okay, so when I want this type of features, bidirectional features in the charger, I will be using this, and on board always we will be having bidirectional feature requirement, because we will have some excess energy in the motor which can be recovered and charged, used to charge your electric vehicle battery bank, which can increase the range, or it will be providing optimal use of the energy which is present on board. Till now we were discussing about non-isolated DC-DC converters. Okay, so what are the types which we have seen? Buck, boost and buck boost converters we have seen. All these four belongs to the second order systems. Why? Because they had one inductor and one capacitor, two charge storing elements, so they were second order systems. Now in this case, what are the demerits of this buck and boost converters? Okay, so here in this buck converter we have seen that the inductor was connected to the output stage. Average inductor current was equal to the output current in this case. Okay, so in buck converter the source current is discontinuous. Is this correct? When the switch was closed, then your inductor was experiencing a voltage which was equal to difference between the input and output voltage. When the switch was disconnected, your inductor was feeding the energy which is stored inside it to the output stage, and the input was completely disconnected. So, my source current is discontinuous over here. When I talk in terms of boost converter, in this case the source current was continuous. Why? The inductor was connected in series with the source, whether the switch was in the on condition or off condition. In both the cases the source was connected in series with the inductor. So, your source current was continuous, but load current was discontinuous. Why? The inductor was, whenever it was charging, the diode, it was disconnecting the path, or the source and the load were disconnected. So, here the source current becomes continuous, but the load current was discontinuous. Same condition is true for this also. So, these are the some of the limitations of this one, that is either your source or load current becomes discontinuous because the inductor and capacitors are selectively connected between the terminals. So, to address the challenges of this one, we had the higher order DC to DC converter which were in the non-isolated domain. Okay, the non-isolated fourth order DC converters are there, where both the source and load current will be continuous, but still it has limited voltage gain. That was, the gain was limited to 3 to 5 times. So, what are the limitations of this family of converter? Whether we go for second order or fourth order, we will find some limitations with the non-isolated DC converter which are listed over here. First is, input and output are not electrically isolated, they are electrically connected. What is the meaning of that? I can start from the source point, I can reach to the load point by following the electrical paths. Okay, so there is no isolation or there is no breakage in the electrical path. So, why this is required for us to what is the meaning of isolation in this one? Okay, so this is done for safety of your electrical components to avoid any events of shocks. Okay, so if we have isolation in between, so one part of the circuit will be completely electrically isolated from the other part. So, we will have facility of providing different grounds. Okay, so what are those? We will see that in the next slide. Whenever I connect one single terminal to the ground, the entire circuit will be grounded. In this case, we will not be able to differentiate the voltage in two different part of the circuit. Okay, so or two different groundings will not be possible because the isolation is missing in between them. Okay, so what is the solution? Can I use this non-isolated circuit having the isolation? Yes, that can be done. How it can be done? I can connect a transformer wherever I had AC at my input stage. Suppose I am using this non-isolated DC converter to design and charger. So, I will, what stages will be there inside the charger? AC to DC converter, then we will have DC to DC converter. Okay. So, now in this case I am not going for isolated DC converter. Suppose, so I can use a transformer here which will be the grid followed by the transformer, and then I can have this converter. Okay. So, I can have the requirement of isolation by using a 50 Hz transformer at the grid side. But what will be the limitation of this 50 Hz transformer? It will be very bulky because the transformer size is inversely proportional to the switching frequency. If my frequency is less, so it will be having a bulkier size, or the core size will reduce when my switching frequency is higher. So 50 Hz transformer, obviously it will be bulkier in size. The transformer, what advantage we get in the transformer, there is no electrical path. If you remember, the transformer will have a magnetic core. Okay, so we will see that in the next slide. So there is no continuous electrical path between the primary to the secondary side of the transformer. We have a magnetic path in between. Okay, so the transformer is can be the best component which can provide isolation in our power electronic circuits. Okay, so we can use this on the AC side, but it will be having a bulkier size because the frequency is at 50 Hz. But when we use it on the DC to DC converter stage, we will be operating at very high frequency transformer, which will be having a smaller size compared to a fundamental frequency or the line frequency transformers. Okay, thus the transformer will be bulky, heavy and expensive. So it will be unnecessarily increasing the converter footprint. What is the converter footprint? The size occupied by your converter will be increasing because of this transformer. Now, what if I provide isolation in the DC to DC converter? Okay, so here now first let us understand what is the meaning of isolation from these two circuit. Okay, so this was our first example of non-isolated DC to DC converter which we have considered, that is our buck converter. Okay, in this buck converter circuit, if we see, I can directly travel from the source to the load side through the electrical path. There is no breakage in this one. Okay, so but when I consider this is the first and the simplest example of your isolated DC converter, here if I see, I am not able to travel from the source to the load side to the electrical path because there is a breakage over here. Here we have magnetic path, not an electric path. Okay, so isolated DC converter, it means there will be a breakage of electrical path, that is we cannot travel from the source to the load side through the electrical path itself, whereas in non-isolated we can directly travel from the source to the load by the electrical path. So it will be continuous. So here we can have two different groundings. Okay, so because the circuit is isolated, we have a transformer in between, the potential or the grounding voltage at the different side of our transformer can be different. Okay, so that's what is the main advantage of your isolated DC converter. They will be providing isolation between the primary and the secondary stage of the converter. Okay, now what are the examples of our DC to DC converter, isolated DC converter, which we will be covering in this lecture? Flyback, forward and dual active bridge. Okay, so in between that we have push and pull and full bridge converters, which we will not be covering because of the limited time. So we will be seeing these three types of our isolated DC converter in this lecture series. Okay, now what is the advantage of using the transformer in the switching stage? We have already discussed this. When I am using it at the switching stage or inside the DC to DC converter, the transformer will be designed for a higher frequency of operation. It will be in the kilohertz range. Okay, not in the 50 to 60 hertz based on our grid power supply. Okay, so they will be not an power transformer, or they will be not operated at line frequency, they will be operated at high frequency. Okay, so when I operate the transformer at high frequency, its size will be very less. When the frequency increases, size will be less. Okay, so the more and more frequency of the transformer operation, less and less size will be there, or your converter footprint will be decreasing. Okay, so it operates at a high frequency, because of that size will be very less. Then compared to lightweight design, because the transformer will be the heavy equipment inside the DC to DC converter. Now we have reduced the size of your transformer, footprint will be reducing. In turn, our converter weight as well as area occupied by the converter will be reducing. It will provide improved efficiency also, greater design flexibility. Now while discussing our basic non-isolated DC converter, we have seen that its voltage gain was limited to 3 to 4 times or maximum up to 5 times. Okay, so when we go for basic non-isolated DC converters, the voltage gain or the relation between your input and output will be anywhere between 3 to 5 times of the voltage. Okay, so we cannot obtain any higher amount of gain. Okay, whereas in this type of isolated DC converter, we will see that just by adjusting the transformer turns, I can achieve any amount of gain as per my requirement. Okay, so now let us start our discussion with our flyback converter. Okay, so before going into the flyback converter, let us discuss on this component, which is our transformer. Okay, so first, if somebody asks Can I use a transformer in a DC circuit? The answer is no. Why? In DC circuit, what will happen to the transformer? Suppose I have connected a DC supply to the inductor. For example, for a simple example, just consider a simple inductor which is permanently connected to an DC source. What will happen to the current over here? It will continuously increasing, or the energy stored inside the inductor will be increasing. L square, it will be continuously increasing. Okay. So, up to how much this relation will be true? Till my transformer core gets saturated. Okay. After my transformer core is saturated, it will not have this relation, it will start behaving like a conducting wire, and ultimately we will have a huge amount of current through the circuit and it will be damaged. Here transformer is nothing but an coupled inductor circuit. Okay. When we will have this relation between the input and output, which we have given in terms of the turns ratio, that is V1 V2 equal to N1 by N2. So, that will be true only when my transformer core is not saturated. The moment I saturate my transformer core, it will no longer behave like a transformer, it will just behave like a conducting wire, and your transformer may be damaged. But ironically, we are using a transformer in the DC circuit over here. Whenever I use the transformer in DC to DC circuit, I should make sure that the core of this transformer never goes into saturation. Okay. So, by some mechanism, if I am able to ensure that the transformer core is never saturated, I can use that inside the DC to DC converter circuit. Okay. So, that is the basic idea in the design of your isolated DC DC converter, that is, we will not allow the transformer core to go into saturation. Okay. So, now the other thing of your transformer is your dot conventions. Okay, so we will see that. Before that, the normal assumptions which we have considered, that is, we are neglecting the losses in the circuit and we are considering it to be perfectly ideal. The switch is turning on whenever the gate pulse is provided, whenever it is removed, it is getting disconnected instantaneously. So, the switch is on for DT time and it is off for 1 minus DT time. We are neglecting the turn on and turn off time of the switch, and again we are assuming the steady state operation. Okay. Now, dot conventions. If you see the transformers, we have dots over here. Okay. So, what is the meaning of these dots? Okay. So, now dots transformer, as I said, it was normally designed to operate in an AC supply, or it was meant to change the voltage level of an AC supply. Okay. Now, we are using that in special case where we are using it in the DC to DC converter. So, in AC circuit, what is the meaning of these dot conventions? Okay. So, they are nothing but they give us the sense of the winding, that is, if the one of the dot is positive at any given point of time, at that point of time or at that instant, the other dot will also be positive. Okay. So, because it was meant for AC signals, so this was used, dot convention was used to give us the feel of the sense of the winding. Okay. So, if one of the dot is positive at any given point of time, the other dot will also be positive at that point of time. After half cycle, obviously the polarity will reverse, the dot will become negative, then at that point of time the other dot will also be negative. Okay. So, that is with respect to voltage. If I see it in respect to current. Okay. So, if the current is entering the dot of one of the side of the transformer, it should leave the dot on the other side. Okay. If it is entering the dot on one side, it will leave the dot on the other side at that point of time. Okay. So, why this is required? If you see, that is derived from the conservation of energy. Okay. So, if this terminal dot is positive, suppose, and it is the current is entering, so the power is fed into the transformer. Okay. Now, on the load side, the power has to be removed from the transformer. Okay. To have balance in the input and output power. So, the current should leave in this direction, or it should flow in this direction, or it should leave the positive terminal. Then the power which was drawn from the source via the transformer, it is being fed to the load. Okay. So, when I say the dot with respect to the voltages at any given point of time, if one of the dot is positive, the other dot will be positive at that point of time. When the current is entering one of the dot, it will be leaving the other dot at that instant of time. Okay. Now, by using this dot conventions and our assumptions, that is, the circuit is ideal and we are operating it in the continuous conduction mode and the switch is on for dt amount of time. Okay. So, we are considering the first equivalent circuit when the switch is closed. Okay. So, if I close this switch, what will happen now? This voltage is connected to this node, or the positive of the supply is connected to this node. Okay. So, it means the dot is positive over here. Okay. So, if the dot is positive, we know the dot conventions at any point of time, if one of the dot is positive, all the other dots would be positive. Okay. So, this dot will also be positive. Now, what will happen to the diode? Okay. So, if I see if the other terminal is positive, obviously the other terminal will be negative. Okay. So, this is negative and this is the positive side of my diode. So, my diode is reverse bias. When I close the switch, what is happening? The diode is getting reverse bias and it is getting disconnected or it is offering infinite resistance. So, there will be no current through this path. So, my current will be flowing in this way, okay, or it will be entering the dot terminals. Okay. So, in this case what will happen? Now, there is no one to consume the energy because the output stage is disconnected. So, what is happening to the current which is flowing through this circuit? Okay. So, this current which is entering this circuit will be used to establish the magnetic flux lines in the core, okay, or the energy which is drawn from the source will be stored in magnetic field of the transformer, okay, or we in the core we will be seeing that the magnetic flux lines will be slowly building up when the switch is closed. Okay. So, what will the voltage across the primary winding V1? V1 will be equal to your source voltage. If I see these three components M and V1 and your source are coming in parallel. Okay. So, V1 or the primary side voltage will be equal to Vs. So, V1 will be equal to Lm dILm by dt, then delta ILm by dt, that is I am again linearizing the circuit assuming that there is high switching frequency of operation. So, I can replace the dILm by dt as delta ILm by dt. Okay. Now, dt is nothing but delta t or the turn on time of our switch. Okay. So, if I realize that, so I will see that the energy stored in the magnetizing inductor. Okay, so what is Lm? So, it is the magnetizing inductor of the transformer. Okay. So, if I see the practical transformer, it has various types of losses: winding resistance loss, there will be leakage flux, and there will be your magnetizing inductor and core resistance. Okay. So, these are the components which will be present in the equivalent circuit of a transformer. Okay. So, here for the simplicity of our analysis, we are not considering the other components. Okay. So, what is the leakage inductance? What is the ideal operation of transformer? Whichever flux is produced by the primary side, it is supposed to be linked with the secondary side and participate in the power transfer. But there will be some flux lines which will be closing their path by the individual winding. That is, the flux, suppose it is produced by the primary side, it will not link with the secondary side, and vice versa, which is produced by your secondary side will not link with the primary side, or it will complete its path with the secondary itself. Okay. Then these flux lines are called as your leakage fluxes. Okay. And small inductor value which will be generating this small amount of flux lines are called as your leakage inductance. And the transformer wires are constructed by using your copper wires. So, they will have small amount of resistance. So, that comes in series, which denotes the winding resistance or the resistance of the wire which is used to construct the transformer. Okay. And in the core load side, we will have Lm and Rm. For our simplicity, we have neglected all other components. We are just considering the magnetizing inductor of the transformer. Okay. So, that is represented as Lm. Okay. So, now in this case, the Lm, or what is this magnetizing inductor? It is the one which is denoting the flux lines of our transformer core. Okay. So, if Lm is having some energy, finite energy, that is half L Im square ILm square over here. Okay. So, what is the meaning of that? If it is having some finite current through it, it means the core is having some flux lines inside it. Okay. So, if it is 0, what is the meaning of that? The transformer core is completely reset, or there is no flux lines in the core. Okay. So, as I said in the last discussion, how we are using the transformer in the DC to DC converter circuit. Okay. So, that can be understood from the flux lines also. Okay. So, if I apply suppose NDC continuously to this Lm inductor, what will happen? The flux will slowly build up for every cycle. Okay. Ultimately, it will go into saturation. After that, our transformer may be damaged. Okay. So, in this type of converters, before it gets damaged, so we will build up the flux in one half of the cycle, and in the next half we will discharge it. Okay. So, in this way we will never allow the transformer core to go into saturation, and we are able to use our transformer in DC to DC circuit. Okay. Coming back to our discussion. here in this, for our simplicity, we are just considering the LM component, okay, other loss components of the transformer are neglected. So, when the switch is closed, I have found out that it will be storing an energy delta M, which will be equal to Vs dt by Lm. Okay. Now, delta I Lm when the switch is closed is given by this, and what is the diode current? It is 0 because it is in the open circuit mode, or it is providing infinite resistance. So, the current through this path will be 0. Now, the complementary state of operation when I disconnect the switch. Okay. So, what was the current flowing through this? It was entering the positive terminal. We know the behavior of our inductor. Okay. So, Lm is nothing but it is an inductor by default. It is, although it is coming from the transformer core property, but it is inductor. So, it will have the similar behavior that it will try to maintain the current in the same direction. So, when I disconnect the switch, it will try to force the current in this direction. So, how it will be flowing? It will flow through this path. Okay. So, now this will be the equivalent circuit. Now, I have disconnected the switch. So, it is having infinite resistance. So, it will flow through this path and complete its trajectory. Okay. So, now what will be the value of V1? So, now if from the dot conventions. Okay. So, in the previous case my inductor was having this polarity, okay, and the current was entering through it. Now, I said that it is the maintaining the current in this direction and it is behaving as a source. So, obviously the positive terminal will be over here, the dot will be negative. Now, this dot will also be negative and this dot also will be negative, because at this point of time when the switch is disconnected, my dot has become negative. So, all the dots will be negative at that point of time. So, if this is negative, now can a diode conduct? So, if I see the other terminal positive, yes, the diode P side is connected to the positive of the supply. So, this diode can carry the current. Okay. So, here if I see this current was flowing in this way or it was leaving the dot over here. Okay. Here in this case, if I see, it is entering the dot, okay, and it is circulating to this path. Okay. So, whether I see the voltage dot convention or the current dot convention, the current is leaving the dot on one side and entering the dot on the other side, and the voltage terminal, or the in terms of voltage, all my dots are negative at this point of time. Okay. So, we will continue with this discussion. Okay. So, what we have seen till now. So, we have started our discussion with non-isolated DC-DC converter. We have seen 3 different types of non-isolated DC-DC converter. Then we have started our discussion on isolated DC-DC converter, which addresses the challenges of our non-isolated DC-DC converter. That is, it will provide isolation between the input and output stage, and it will have and flexibility in the transformer turns ratio design, which will be giving us an unbounded gain relation. That is, it is no longer restricted between 3 to 5 times as our non-isolated DC-DC converter was. We can attain any amount of gain between the input and output voltage by adjusting the transformer turns ratio. Okay. And we have started seeing our first isolated DC-DC converter, which was our flyback converter. We will continue our discussion from this point in the next class. Thank you.